Welcome, everyone. Thank you for coming. And today we're very happy to have Hamza Patmanavan visiting us virtually, of course, from the University of Geneva, where she's a scientific collaborator too and a PI of a Swiss National Science Foundation Ambizione grant. Hamza got her PhD at the Inter-University Center for Astronomy and Astrophysics in Pune, in India. And she held postdoctoral positions at ETH Zurich as a Tamala Fellow and at the Canadian Institute for Theoretical Astrophysics as a CETA Fellow, as well as Dunlop Institute in Toronto. Hamza has very wide interests within astrophysics, both in theory and observation. Some of the theoretical work, in fact, she's done with collaborators here at the CFA. And she's, as an observer, she's part of the DESI, SKA, and COMAP intensity mapping collaborations. Hamza is a world expert on the field of intensity mapping, and I really look forward to hear what she's going to tell us about cosmic dawn and intensity mapping today. Before handing it to Hamza, I want to kindly remind you to mute your microphones if you don't actually want to speak, so we minimize noise. But Hamza has encouraged everyone to please ask her questions throughout the talk if you want. So with that, Hamza, please take it away.
Thank you so much, Julian, for this really kind introduction. And thank you to Lars and Randall and for the kind invitation so many months ago. And it's great to be here, great to be back. And I do hope we can have the chance to meet in person sometime soon, in a few months, hopefully, with the COVID coming down. What I'd like to talk to you today about is based on several pieces of work, which together point to how we can extract probably the most precise, most accurate constraints on cosmology and even fundamental physics by using the information in the astrophysics of systems between today, the present day, all the way up to what is known as the final frontier, really, of the observational cosmology, which is the cosmic dawn, the time when the first stars and galaxies formed. And this is all going to be on how we can do this with the help of baryonic material. So to give a brief idea, an introduction to what we're going to be talking about, probably everyone here in this room has seen the picture on the left, which is just showing you what a strange and weird composition our universe has. The kind of stuff in baryons, the kind of stuff which we know and we kind of are made up of and we interact with, are just about 5% of the observable universe, with the rest 95% made up of these exotic material, which we still don't have an understanding of, a full understanding of. And what is very important to realize from this picture is that we only have this as a probe to understand all of this, at least at the present time, with dark matter not having been discovered yet in the lab and so on. But if this picture humbles you, because, you know, we're not the only planet, we're not the only solar system, we're not even made up of the most dominant component of the universe, what is even more humbling is the picture on the right, which probably not so many people have seen. And this is really the way this 5% itself is divided up in today's universe. What that tells you is also very fascinating. It shows us that the kind of stuff of baryons which we are actually familiar with in day-to-day life, which is to say the planets and stars and so on, which we are interacting with and we call baryons, are only 9% of this 5%. They're like less than 10%, and that has been the situation for at least about the last 10 billion years. The rest of the baryons are and have always been, for a large extent, in the form of gas in different forms, not in stellar or star-like material. So this is gas in the form of, like, we have something called the Lyman alpha forest, which is essentially neutral hydrogen, hydrogen being like the most dominant gas. Then we have gas at different temperatures, emitting in X-rays and other species and so on. There are a little bit of controversies on whether there is some gas in the circumgalactic material and warm, hot intergalactic medium and so on. But most of the material, to a large extent, has always been gas. And therefore, the study of baryons, the study of the evolution of the universe in this in this context has to be really the study of this gas. And when we look at it, we find that there are two major phase transitions this gas went through as it evolved across the universe. So if you're looking at a brief history, we know that essentially around 300,000 years after the Big Bang, you had this recombination and decoupling, which is when the CMB sort of broke away from the neutral gas. And this sort of led to a period known as the dark ages of the universe. So dark because apart from the slowly fading glow of the CMB, there were no luminous sources lighting up the universe, and we just had the neutral material. And the dark ages came to an end. They lasted for about a few hundred million years, and they came to an end with the switching on of the first luminous sources, the first stars, the first black holes. And it led to a period which is known as cosmic Renaissance, just to draw a parallel between the Middle Ages and the Renaissance. So it's called also the cosmic dawn, or the formation of the first stars and galaxies. And what is really exciting is that these first luminous objects turned back the majority of this neutral material into protons and electrons, so putting it back into the state it was before the decoupling and before the recombination. And today, and for the last 1 billion years, last 9 billion years, we're seeing a really highly reionized universe. So this is very exciting, and it kind of tells you that there are a series of milestones which this baryons went through. And as cosmologists, or when we want to look at this from the point of view of constraints on our theories and laws of physics, then there are some very salient questions that you can ask at each epoch of the universe. So at the time when the universe was already reionized, all the way up to 1 billion years or so after the Big Bang, the most salient question is, can we look at this gas, and which is between galaxies and some within galaxies, constraining astrophysics and cosmology. Now, cosmology, very importantly, because it's the time when you had the dominance of the dark energy, for example. So people are interested in using this material to constrain the evolution of cosmology. If we go a little higher and we're kind of thinking about the time of the cosmic dawn, reionization, and so on, then a very pertinent question is, how did all this start? How did the first black holes form? And how can we model the evolution of this second major phase transition of all the cosmic baryons, of almost all the cosmic baryons? And if we want to get really ambitious, and we're going right up to this period of cosmic dawn, dark ages, and beyond, then an extremely exciting question we can ask is, how can we use all this material, and especially this plethora of information in baryonic gas, to enable the most precise constraints on fundamental physics? Because this really is the data set of the future, and it's the biggest data set we're ever going to have. So needless to say, there are a huge number of observational efforts going out to measure and map the evolution of the baryonic material in different species and at different times in the evolution of the universe. And prominent among these are some of the efforts in the 21 centimeter line of neutral hydrogen, which kind of tells you about the evolution of the most dominant component. These are some of the examples of such experiments. And one of the biggest ones is going to be the square kilometer array setting up in Australia and South Africa. These two lines, the last two lines, tell you about similar such efforts in sub-millimeter, such as the carbon monoxide and another species, which is singly ionized carbon, which are also excellent tracers of the interstellar medium and star formation, and play a great role in mapping the evolution of these baryons. In recent times, a technique which has come to be of great interest for doing all this and for looking at these baryonic species is known as intensity mapping. Intensity mapping actually has quite a long history. It was first suggested by people all the way in the 1970s and even before that, when they sort of looked at intensity mapping as a way by which you can get information out of the diffuse large-scale structures sampled in baryons. Briefly put, what intensity mapping does for you is to go from a picture like this to a picture like this. So on the left-hand side, what you see is a galaxy survey, a traditional galaxy survey where you have individual objects, and these red points show you the kind of depth you'll reach with, say, a VLA survey, which is going to pick out kind of the brightest objects. And obviously, this takes some time because you want to target each of these objects and you want to measure their properties individually. But in intensity mapping, you don't do that. You look at the same patch of the sky, and then you look at it in the integrated emission of the radiation. So for example, if it's carbon monoxide, you're just looking at the radiation like you looked at the CMB in photons. Intensity mapping, therefore, is much faster and more efficient way of probing these large scales, which are relevant to cosmology. And what is interesting about it is that you can do so in different species. So like I said, there is the hydrogen, which is observable in terms of 21 centimeter transition, which probes like the largest scales. And at smaller scales, you have these sub-millimeter lines like the carbon monoxide and ionized carbon, which probe smaller scales relevant to star formation and the interstellar medium. And right from 1972, this has been kind of going on, and we already have our forecast for the 2050 surveys, which are very ambitious. And what they're trying to say is that we use intensity mapping like a series of CMBs between us and all the way back to the CMB to look at all these different baryons and different species. And not only for astrophysics, you can do so much cosmology with this technique. And the favorite line by far is the 21 centimeter. And what you see here is a sort of illustration of how powerful this technique is, because it reaches down to like the gene scale of the emitting material. So it's not affected by silk damping and other things, and it probes a large number of modes. And this is essentially a picture from these people who showed us that when you look at the co-moving volume of the universe, then the current surveys like the SDSS or even the most surveys going up to redshift of 1 and galaxies, they probe a much smaller co-moving volume than what you might be able to do if you were able to get into the dark ages, and this by quite a few orders of magnitude. And when you combine all this, and when you look at how you can get modes up to the gene scale and so on, you find the kind of Fourier modes, the kind of independent components of information, which you have in these kind of baryonic surveys, is orders and orders of magnitude higher than what you have today at the CMB and galaxy surveys. So definitely being the most largest data set, we need to extract the best constraints on both astrophysics and cosmology from this technique. But it has its own challenges. And one of the challenges which I'm going to kind of spend a little bit of time on, which can be both a blessing and a curse really, is what one would call the astrophysical systematic in any of these kind of surveys. So what it means in a nutshell is that you have a map, an intensity map like the one I showed you. And what you derive from it is essentially something like what you have from the CMB, which is known as a power spectrum. And the power spectrum contains two salient components. One of them is called a clustering term and another is called a short noise term. But what is very relevant to note is that both these components, they contain parts of both the astrophysics of the underlying tracer, for example, the hydrogen or the carbon or whatever is emitting, and also the cosmology, which is like the dark matter, power spectrum or the evolution of the Hubble parameter and so on. So there is this intertwining of astrophysics and cosmology in every one of these intensity mapping surveys. And this really needs to be modeled and quantified if we are to use intensity mapping to do cosmology, and also if we want to use it as an astrophysical data set. One of the most natural ways in which we have found this to be possible is to use a method which has been very successful in both studies of galaxies as well as in the underlying dark matter halo itself, which is known as a halo model. And essentially, this is a way by which we want to go from the underlying dark matter, which has been quantified in terms of the halos and their abundances and their clustering, to the intensity map, which is essentially baryons and how these baryons are populating these dark matter halos. So this problem is something we spent some time on looking at from the point of view of both data and theoretical perspective. What we found is that in order to go from the dark matter halo model to a data-driven framework to understand the baryonic abundances and clustering, you essentially need two main ingredients. So the first one is called here in the case of hydrogen, I call it MH1, but it can be any function of the underlying tracer, but importantly, as a function of the mass of the halo and the redshift of the halo. So this function is made up of 3 free parameters in the case of neutral hydrogen. And all these 3 have interesting physics associated with them, which I'll come to in a few slides from now. The other ingredient you need for doing this kind of approach is called the profile. And the profile essentially tells you how this gas or this baryonic material is distributed as a function of scale. So it's just like your NFW, that kind of profile. And it introduces for you a couple of free parameters, just like the dark matter halo model does. So in order to constrain the parameters of this kind of framework, we need to look at the data available to us. And interestingly, this data naturally divides itself into 3 main classes. So at the very local universe, or the kind of low redshifts, you have traditional galaxy surveys. So these are some examples of surveys which go out and measure individual systems, individual galaxies, and their clustering and their column densities, for example, which are all statistical quantities. At intermediate times, we had very interesting experiments, and we're still having actually this, there are experiments taking place which are cross-correlating different observables, like the intensity map in, let's say, 21 centimeter with galaxy surveys. And but they have up to now gone only up to redshift of 1 or so. That's the kind of number. Whereas when you look at redshifts which are higher, you essentially have a huge amount of data in the neutral hydrogen, which is available to us not in galaxy surveys, but in what is known as damped Lyman alpha systems, so DLA systems, which are known to be the highest reservoirs of neutral hydrogen between, redshift of say 1.5 to 5.5 and even a bit beyond. So what is interesting is that if you take all this data together, you're able to recover pretty tight constraints on the baryonic gas on the 21 centimeter or the neutral hydrogen halo model, which this is kind of the functional form for these halo model parameters. We don't have to pay too much attention to it right now, but I'll come back to it in a few slides. What is interesting to note from this figure is that using a Markov chain Monte Carlo, we're able to get constraints on this 5-parameter framework from a bunch of data which are pretty independent, which are not measured the same way and do not have the same systematics and so on. So that is very encouraging, And what is more encouraging is that it kind of fits a huge, range of redshifts. So what you see here is that between redshifts of 1 and say 5, you have these different kinds of observations which are measuring for you the abundance and clustering of these systems. This is in the DLAs. Whereas around redshift of the similar redshifts, you also have the intensity mapping experiments, which are going out and measuring like the large scale, clustering and so on. And both of these, this is just a snapshot. So all of these are very well fit by the model. This is not surprising at first sight so much because the Markov chain Monte Carlo is designed to fit these parameters. But what is very gratifying is what is shown on the right-hand side of this black line. And what is shown here are examples of data which were never fit to the MCMC in the first place. So these are data in neutral hydrogen coming from imaging surveys. There were a few observations which kind of told you about the surface densities and so on, covering fractions of DLA systems, and they fit right out of the box. So that gives us a lot of confidence in these parameters as the dominant ones, capturing the dominant processes. And what is more, it leads you to a very well understood or well sort of constrained relation for both the H1 to halo mass as well as the way the profile works as a function of scale. There are a couple of salient features worth noting about the best fitting model. And one of them is that it's a manifestly non-unity slope. So the H1 mass is not proportional to the halo mass, which one might have expected naively because that would be very natural. But there is evidence for it to drop at the higher mass end, and this turns out to be important in the upcoming slides. The other interesting thing is that the profile is manifestly exponential, which is reminiscent of disks, and that's also very physical, and it has a kind of scale radius or a concentration, which is typically galactic. It's like about a few 10 kpc. What is more interesting is that not just the fitting of these various observables, we gain a lot of interesting insights on physical parameters governing gas and galaxy evolution from the way these parameters work. So if we want to look at that in a little more detail, we should take the way the H1 mass to halo mass is parametrized in terms of these three free parameters and look at them one by one. So the first parameter is alpha, and alpha sets a normalization for the neutral hydrogen in dark matter halos. So forgetting about the rest of this, alpha just tells you how much of a fraction of neutral hydrogen you have relative to the cosmic fraction. This is a cosmological fraction. This is like dependent on the helium fraction and so on. But this one just sort of gives you an up-down normalization on that. The number you get from the best fit is like 0.1, 0.09. And it's an interesting number because it is reminiscent of several studies, especially in the recent literature of observations and simulations, which showed us that the fraction of cold gas in these galaxies is indeed roughly 10-20%. You'll notice that there isn't a function of Z in front of alpha. This was not by design. We did allow it to evolve, but it stubbornly refused to evolve given this current data. Looking back, this is very reminiscent. This is indeed physical because it tells you about something people have been commenting on a lot, especially with respect to DLAs, and that's the non-evolution of these disks. So for example, what people were saying is that there is a balance of the accretion of the H1 and its consumption for the star formation. And that's what's been playing out in this alpha, not varying so much as a function of redshift. The second parameter is called beta. And like I mentioned briefly, it's like the slope. So for example, if this parameter was 0, then the H1 mass, which is on the left-hand side, would be proportional to the halo mass with no further powers. However, this beta has a very interesting history because historically, people used to look at these neutral hydrogen observations in the context of galaxy surveys, which were being done at that time, as well as the damped Lyman alpha, which was also being done at a completely different redshift and epoch, right? So what was interesting is the kind of models which were used to describe the 21 centimeter kind of observations, which probed very low redshifts, and the damped Lyman alpha observations, which probed like the higher redshift, were very different. You can see that they are very different in the literature. In one of the early studies, we decided to kind of bring together these models at face value and just see what happens and what they kind of, what they describe. What we found was interesting. We found that actually a model which combines them does do pretty well at matching all the data, but it doesn't do so good when you look at the H1 mass function. So this is just telling you something like a luminosity function. You can see that it's kind of over predicting here and under predicting here. And what the Markov chain Monte Carlo taught us was that the beta parameter is really needed for getting this to do a good job. And with error bars, it does match almost completely. And it is very physical because it's related to these effects people have been seeing in simulations a lot, the quenching and the feedback, which kind of drives the neutral hydrogen out of these massive halos. There's some quenching going on, and H1 doesn't really exist. Neutral hydrogen doesn't really exist in these big halos. So that's very exciting. And the third parameter also has a story to tell. So this is called the VC naught, and VC naught is a virial velocity. So as you can see from the form of this expression, this sets for you a lower cutoff. So it tells you about what kind of dark matter halos preferentially don't host neutral hydrogen. And the number you get for this cutoff is something like 36.36 or 37. At first glance, this number might not seem super intuitive, but what is quite interesting is that when you look at it from the point of view of photoionization, there have been studies in the literature ranging from 80s and beyond, which looked at analytically the formation of dwarf galaxies by the suppression of these formation by the photoionizing background. And what they found was interesting. They found that if you look at a typical virial velocity and formation of these galaxies, and you put in the kind of ionizing background which was present then, the circular speed at which this suppression occurred was about 37 kilometers a second. So it's amazing that data in 2017 completely confirm to this analysis, and it gives you confidence that indeed these galaxy suppression is happening on the scales that it should. Now, this is quite interesting in terms of astrophysics and connecting to observational parameters, but you can also do a lot of interesting cosmology with this kind of framework. So the way you would do this is that you would look at the 21 centimeter, or in general, any of the power spectra, the way you do for the CMB. So in the CMB, we have this CL, which is the angular power spectrum in these redshift bins. And this, in the case of 21 centimeter, would be a similar kind of spectrum, but it would have, as I mentioned, both the cosmology as well as the astrophysics. And completely coincidentally, the astrophysics of the neutral hydrogen also has 5 free parameters, just like the cosmology, but of course that was not by design. And it might well have more parameters in the future. But what is interesting and what is really relevant here is that you can impose realistic priors. That's because you are looking at all these parameters in the light of all the data we have so far. So it absolutely represents your current knowledge. And then you can use a Fisher matrix formalism to derive cosmological constraints. So shown here are some of the constraints you get with the help of, with both the astrophysics and cosmology thrown in. You should ignore the values on the y-axis because these are, these numbers are bound to change with the help with foregrounds and other quantities. But what is important to note from this figure is that if you have an astrophysical systematic, then it does degrade your cosmological forecast a bit. But what was very gratifying is that if you have experiments like especially the CHIME and SK and experiments which are reaching a large redshift coverage, then we found that this degradation is almost completely canceled or alleviated by the fact that all these different Fisher modes are being combined. So this is a very interesting result, and it shows you that really the power of the intensity mapping to do accurate constraints. You can also do other interesting things. You can do cross correlation. So for example, we have the CHIME survey, which is already taking data, and its cosmology part should be starting soon, and DESI, which is going to be starting up as well, and is focusing on the optical part. So for example, what we found is that if you have a cross correlation between the CHIME and the DESI map, then in principle, you can get much better constraints on the cosmological and the astrophysical. You can see both the neutral hydrogen parameter and the galaxy parameters at a level comparable to autocorrelation of SKA, which is of course a very unfair comparison because by the time SKA is around, you will have LSST to cross-correlate with. And indeed, we found that doing that kind of cross-correlation gets you even tighter, better constraints on these parameters. So you can do even more by looking at how beyond lambda CDM, more fundamental physics, effects can be constrained with the help of intensity mapping. And one of the interesting points to note in this context is that up to now we were looking at precision of the constraints, the cosmological constraints, but it's also important to be accurate. It's important to be, at the right value and not just very precise and off. So what is used for this, the details are not relevant, but just in a nutshell, is something called nested likelihoods framework, in which essentially what you do is to look at how much does the bias on a particular observable change just because you've made a mistake in another observable which is correlated, right? And this is very useful, not just for looking at the accuracy, but also for asking if there are effects beyond the standard lambda CDM, such as primordial non-Gaussianity. Primordial non-Gaussianity is the quantity that makes CMB maps, which should look like this, if the primordial non-Gaussianity was very high. But for sort of reasonable values, there's a way by which you can quantify the effect of this primordial non-Gaussianity on the bias of the large-scale structure. And when you do that, you can very easily use the halo model framework for the baryons for neutral hydrogen to ask what kind of bias you would incur on the primordial non-Gaussianity if you made a mistake in your astrophysics, if you had an astrophysical uncertainty. And what is very gratifying is that even if the astrophysical uncertainty varies throughout the values, it is allowed to vary, the effect on the primordial non-Gaussianity is within 1 sigma. So this is good news for most of the science cases for detecting this. And so this is all about the neutral hydrogen and what kind of cosmology and astrophysics you can do. But we can also look beyond the LCDM in the other direction. Like, for example, you can even go from the hydrogen towards the dark matter. So you can probe the nature of the dark matter by asking if there are these fuzzy dark matter kind of candidates. And we find that those can be constrained at few percent level just by the effects on the power spectrum and putting in the astrophysics of the H1. And that's very exciting because that's better than what most of the current experiments can go down to. And we can also do this with other lights. So as I mentioned, that we have these other tracers of the baryonic universe, especially at high redshifts, which are the carbon monoxide and the C+, which is the singly ionized carbon. And both these traces are very interesting because these are salient probes of the interstellar medium and of star formation. So together with a collaboration known as COMAP, which is led out of Caltech and contains a large number of institutes, we are looking at the CO transition at the epoch when star formation occurred. But since the carbon monoxide has a ladder of states, it's also going to be sensitive to the carbon monoxide at a redshift like closer to reionization. And that's very exciting. And in these two papers, I essentially looked at how we can use the same kind of techniques, similar parametrizations, to ask what kind of luminosity functions can be constrained for both the carbon monoxide and C+ in the context of intensity mapping. So for example, you can figure out how the luminosity and halo mass relation is constrainable using all the data. And this turns out to be quite consistent with most of the current, most of the simulations and so on. And similarly, you can also look at the C+, which is the singly ionized carbon. And that's being hunted down by several experiments in the near future. And today's data tells us that we probably have a good promising outlook for several of them. The carbon monoxide at the epoch of reionization leads you straight to what we were kind of trying to go to in the first place, which was the first galaxies. And the first galaxies at redshift of 6 and so on, essentially are studied in full only by looking at also the formation of their black holes, which is a really challenging problem in astrophysics. And it has a huge amount of influence and consequences for the epoch of reionization. So what is very interesting in this context is that when you're looking at these galaxies and you're trying to bring them into a parametrization of the baryonic physics, the way their stellar masses or their neutral hydrogen, for example, varies with halo mass, as you see, is not much evolving. So you see like between redshift of 0 to redshift of 10, you don't see that much evolution in the stellar mass to halo mass. And this is coming from a lot of data. It's just a data-driven framework like we did for the hydrogen. However, if you look at the way the black hole masses are evolving with halo mass, it's really high. It's much, it evolves a lot more. And that has been parameterized very effectively by some of these people by looking at their circular velocities and so on. And what is very important is that at these high redshifts, you get a very interesting signature of these systems in gravitational waves. So this really brings you to the power of the multi-messenger. And the forthcoming LISA observatory, and probably a few years before that, the pulsar timing arrays too, if we're lucky, would get you constraints on these first galaxies through their gravitational wave emission of their individual black holes. And the kind of numbers you're looking at with LISA, for example, are between about 10 to the 4 to 10 to the 7 solar masses. So here is a very interesting picture coming from the Astro 2020 science white paper, Monica Colby and other collaborators, which shows you the kind of sensitivity that LISA, for example, will have for these galaxies right up to the epoch of cosmic dawn and even beyond. So these symbols show you like the highest redshift detected GRB, the highest redshift galaxy, the highest redshift QSO, and these periods which are salient like cosmic noon, reionization, and so on. And it also shows you the signal to noise of the LISA survey for merging black holes at all these different epochs. And what you see is that even up to the time of cosmic dawn, there is reason to be optimistic with these surveys to constrain the evolution of the parameters. So how do we kind of do this and bring it into context? So the way by which this black hole to halo mass halo model can be used is that you look at the merger rates of the dark matter halos. So you look at the way these, so this has been parameterized in the form of simulations from a long time, but the latest studies show you quite a unique way of characterizing this. And then you can bring in the halo model framework of the black hole to halo mass to figure out that you parameterize the merger rates themselves in terms of what we would call known and unknown parameters, which play similar roles to this astrophysical and cosmological, in that the known ones are the ones for which constraints by LISA and other surveys have fairly well sort of told you the kind of uncertainties which you might expect. But this unknown are really parameters coming from the astrophysics. Like, for example, this denotes an occupation, this denotes some kind of normalization and slope and so on. And therefore, we have to do the same thing. So in this way, however, in this case, when we have constraints already on known parameters, what is quite easy to do and also gives you a lot of good insights is that you can use the way the masses and like the mass fractions of the merging black holes at high redshifts by extrapolation are constrained by LISA to adapt and modify the standard Fisher matrix technique. So the equations here are not that relevant, but what is really salient about this way of doing things is that you look at a three-dimensional set of variables. So you have to imagine a four-dimensional space here. You have the three parameters, let's say the mass of the black hole, their Q parameter, the ratio, and the redshift, which together give you the rate at which these mergers are happening. And then you can use the existing constraints on these parameters to develop a constraint on the final merger rate. And then you can normalize it to the number of events you expect and so on. And so essentially the kind of Fisher matrix which you had with CL versus L, you now have three variables on the effective x-axis. Turns out that the math goes completely as it should, and you can end up with very good constraints on astrophysical parameters as well, even to sub-percent levels. So this is around redshift of 8, and this is what we found in this paper, that if you take this Fisher matrix, then given the fact that we'll have these constraints from LISA, we can do really well in terms of the astrophysics of the black holes. So now that we have all these different constraints coming from different parts of this evolution of the baryonic universe, we should follow the distinguished Harvard alumnus Stephen Covey and bring them together. And that really seems to be the way forward for large-scale surveys of baryonic gas right up to cosmic dawn. So here, is a snapshot of what we can do potentially with combining all these different observables in a parameterized statistical framework. So for example, you can do with intensity mapping, neutral hydrogen. For example, at these intermediate scales, you can go after the carbon monoxide and relate that to the way star formation is taking place in the intergalactic interstellar medium. And a little further out, you're going to definitely have targeted galaxy observations. But most importantly, you're going to have the connections between the black holes and the dark matter halos. So bringing them together really represents probably our best attempt to exploit this wealth of data taking place across these this huge number of redshifts, and in so doing, give us very good constraints on fundamental physics. So right now, there have been already so many efforts to think about how we can do fundamental physics from the cosmic dawn, right from variation of fundamental constants to different kinds of dark matter, dark energy, and several others. And we found, and we say something about this in this paper, that when we look at this from the point of view of astrophysics, so when we look at the astrophysical systematic and we try to model this efficiently and do cross correlations, we probably will have a very good chance to even go beyond lambda CDM, and that too all the way at cosmic dawn, which we summarized here in a chapter for the square kilometer array on fundamental physics from the square kilometer array, which is a very ambitious title, especially looking at the cosmic dawn and reionization. Okay, so I think I've kind of closed the loop on how we can answer all these key questions with the help of the wealth of information in the baryonic universe. So let me quickly summarize by telling you that there is an astrophysical systematic effect always when we look at these biggest cosmological data sets. And the most promising way to kind of deal with it seems to be using a data-driven framework such as Halo model. And this is very powerful, not just to look at the precision and accuracy of cosmological forecasts and see how the astrophysics and cosmology are playing out, but also to cross-correlate with large galaxy surveys to look at, for example, also how we could do the sub-millimeter regime like the CO and the C+ lines. And interestingly, such a framework, when combined with treatments for the first galaxies and first black holes, gives you a huge amount of information on their astrophysical properties and potentially also on their formation. So this should be our best shot at getting constraints beyond the standard model all the way from the cosmic dawn. Thanks a lot. Stop here.
Thank you, Hamza, for a great talk. So let's all thank Hamza and think of questions that you may have, and raise your hand if you have questions. On the meantime, I wanted to ask you a little bit about a technical question about the FNL that you mentioned before. How much should we worry? So you showed us that we don't have to worry about astrophysics when looking for this scale-dependent bias. Do we have to worry about foregrounds in any way?
So it's a great question. People have been worried that the large scales, which are preferentially going to tell you about FNL, are also the exact same scales which are going to be probably washed out by the foreground. One of the recent studies, which I think is quite promising in this context, showed that if you do a joint fit to data and foregrounds, the same way as people did for the CMB, then they are able to recover both the FNL as well as the foreground parameters in a very clean way. It's probably the cleanest way that we can expect. So there is probably hope, reason for hope for FNL, but indeed this is one of those which is definitely going to be overlapping with the foreground part. So we have to be careful.
I see. Thanks. Ramesh has a question.
Yeah. Hi, Hamza. Very nice talk.
Thank you.
You have an exponential cutoff at some 36 kilometers per second in your model.
Yeah.
It comes with a third power of the velocity. Where does the 3 come from?
Yeah. So this 3 actually comes from the fact that this cutoff is inherently a mass cutoff, but it's a mass cutoff which varies with redshift in exactly the same way as circular velocity. So as you see, the circular velocity is m to the 1/3 and z to the 1/2 sort of. So therefore the m to the 1/3 and this 3 essentially is what gives you the mass cutoff. So people did model this for the case of DLAs by using circular velocity, but since they wanted to relate it to halo mass, they needed to use the third power. You can equivalently write it in terms of m.
Yeah, I guess I didn't realize that mass goes like velocity cubed. I always thought it was the fourth power, no?
So it's square root of gm by r. So it's the v essentially goes as the mass of the halo to the 1/3, and redshift to something like 1 plus z to the 1/2.
Okay, thanks.
Yeah.
Speaking of this 36 or 37 kilometers per second, does this depend on the intensity of the UV background?
Indeed. So, well, that the thing is that when for sure this number which you get comes because when you look at the relevant UV background for this kind of redshift range, it's kind of flat. It's not changing so much. People used a sort of average number here, and they found something like 37. And what we found is that even if we use the latest Hart and Maddow, then you will get similar numbers. So, but your question is very relevant because in principle, with better data, we know that this is the one which is tied to the UV background, so we can constrain the UV background from this. So that would require exquisite data, but that's how the physics is working.
Okay, very cool, very cool. More questions for Hamza? Okay, well, if not, let's thank Hamza again for visiting us virtually and telling us all these interesting things. And good to see you all.
Thank you so much. It's great being here.